Welcome back to Physics with Miyoshi. Today we're here to talk about uniform circular motion, which is why I am twirling this ball around. And so we're going to talk about all the things that uniform circular motion means. So, let's start. Uniform circular motion, first of all, the definition is that it's a motion of an object traveling at a constant speed in a circular path. So the trick here is that it's constant speed, and of course it is a circular path since we're talking about uniform circular motion. The uniform part meaning the constant speed. So what does that mean? Well, if we have a path described by this circle and we've got a certain radius, like I had with the ball and the string, and I have this velocity, the velocity does change, but we'll talk about that later, but the speed stays constant. The radius is going to stay constant also in this, and we also have this thing called the period. The period is the time it takes for the object to go all the way around the circle one time, just one time. And even though it's not in our particular book, there's this thing called the frequency, which is the time, which is 1 over the period, or it's the time it takes for one revolution. It's the same, it's the reciprocal of the period. So, if we think back to our kinematics, so something back to what we know, we remember that our velocity or our speed is our change in distance divided by our change in time. Well, in the case of a circle, our distance is 2 pi r, or the circumference of our circle, one time around, and the period is just the time. So the speed is our 2 pi r divided by our period. And that just takes it back to, again, our kinematics. Remembering velocity is change in distance divided by change in time. So, how do we use this? Well, in our particular textbook, we have an example of a tire balancing piece of equipment going around a certain speed at a certain frequency of 830 revolutions per minute. Also, you can RPM, if you see that, remember that's revolutions per minute, hopefully. And it's got a radius of 0.29 meters. And so what is the speed that a point on that circle or on that wheel would go around and around as we think about it? So if we think about our d, or going back to our kinematics again, our d is 2 pi r again. So it's 2 times pi times 0.29, which is our radius. And we come up with 1.822 meters. Our frequency, that's our period. That's the thing we have to go way back to the beginning and think about changing our units. Frequency, our period and frequency are reciprocals of each other. So the period is 1 over the frequency, which is 1 over this 830. So I have 1 over 830 revolutions per minute. So I want to change that to seconds. So I have 60 seconds over 1 minute. And so I end up with, take 60 seconds divided by 830 revolutions, and I get 0.0723 seconds. Now the revolution is actually a unitless unit, so I'll just take the revolutions out, and I end up with my period is 0.0723 seconds. Okay? So if I think back again to my kinematic equation, I have speed is distance over time, or my circumference divided by my period. So I end up with 1.822 meters divided by 0.0723 seconds. And I end up with my speed of a point on my tire going around at 25.1 meters per second. So, and that's about it. That's uniform circular motion in a nutshell. Just the introduction, a little bit of the definitions. Remember these pieces of vocabulary, if you will, and think about back to our kinematics. I always tell my class that our kinematics is not going to go away. You're going to keep using them over and over and over again. And think about math a little bit too. The circumference of a circle is in here as well. So we use a lot of application in our physics, of our math in physics. So just remember those things as well. So uniform circular motion, motion of object traveling in a circle at a uniform or constant speed in a circular path. So when you think about and pull on a string, as silly as that might seem. That's uniform circular motion. And we'll come back and talk about that more next time on Physics with Miyoshi. Thanks for tuning in.